Hi everyone and welcome to another lecture. So today we want to continue our discussions of function of operators, and today we would like to start by defining a derivative of an operator. So let me just write it down. Derivative of an operator. So how to make sense of this? Because if you consider a finite dimension, then our operators can be represented through matrices. But derivatives are something that we use to define for functions. So how can we define a derivative of a matrix? So let's say I have some operator, let's call it R, and it's a parameter dependent operator. That is, it depends on some scalar parameter, that is theta. So a simple example is the rotation matrix. So the first entry is not sine, it's actually cosine, but we could have just taken it to be sine as well, but that won't correspond to a rotation like we see in a regular basis. So let me just write this rotation operator, and you can see that the elements are coming in terms of sines and cosines, which will depend on theta. That is, if you take pi by 2, so r of pi by 2 will be something cos pi by 2, which is 0, sin pi by 2 is 1, so there is a minus that will correspond to minus 1, and you will have sine of pi by 2 that will correspond to 1, and finally here you will have a 0. So as you change the parameter, the values in the of the elements in the matrix are also changing. So the idea is to define a derivative of an operator comes from these parameters. That is, since the parameters can vary, we can define a derivative using the parameters. So let me just write the formal definition. That is, for this any operator R, and let's say it's dependent on theta, we can define the derivative with respect to theta. So that's an important point to note, that the derivatives are defined with respect to the parameter. That is similar to taking derivatives with respect to a variable. And the formal definition is just like this. So let's call it del theta, that goes to 0, and you will have this matrix over here that is containing the parameter and a perturbed part, that is delta theta, and here you will have r of theta divided by del theta. So when this limit goes to 0, we can find the derivative. So this is just a formal definition, and now let's try to evaluate the derivative itself. That is, we have our r of theta as so now we ask what is dr of theta by d theta, right? That is the first derivative. So the idea for that is to perturb each of these elements and then taking the limits to be 0. In more simpler terms, this can be done by just taking derivatives of each of these elements. So if you just take the derivative, this will be just minus sine theta, here will be a cosine theta, there will be a minus cosine theta, and finally you will have a minus sine theta. And if you want to evaluate the derivative at some specific point, let's say now I want to have theta equals to pi by 2. So after you take the derivative, as similar to function, you just put theta is equals to pi by 2, and that will give us minus 1, 0, 0, minus 1. So this is how you can easily define and calculate the derivatives of some matrices. In fact, if you are wondering, I have two matrices A and B, and both of them are functions of theta, that is the parameters of theta, and I want to have d theta like this. So the product rule will also apply, and you can prove it using the definition over here, that is the first principle of derivative. So this will just be dA theta b. Let me just put them in parentheses so that you can easily distinguish that the order over here is very important, because dA by d theta will also be a matrix, and b itself is a matrix, and in general matrix multiplication, they don't commute. That is, AB is not equals to BA. Alright, so and here you will have A and dB by d theta. So this product rule will also apply. Okay, and since the derivative is a linear operator, you can also have A plus B as dA by d theta plus dB by d theta, and so on. Now we want to look to another example, and this will also give us some idea about solving operator valued differential equation, and they are particularly important in quantum mechanics and quantum field theories. So let's try to focus on that. So we are taking some operator, let's call it theta right now, and okay, not theta, so that you guys don't get confused. So let's call it b, and it has a parameter of lambda, and we denote it with e to the power lambda omega, where omega itself is a matrix, that is, it's an operator. And the way to take the derivative, because at first it may seem that if you just calculate dB, which is a function of lambda, this should give you the omega times b. This is what you might think, but let's try to check this, whether this is true or not. So we want to put a question mark over here. So is this true? Because that is something coming out of our intuition. That's just it. And we want to see whether this is true or not. Again, b is a matrix and omega is a matrix, so we really have to check whether it's omega b or b omega or completely something else. So we have to be very careful on that. So the first step is to write dB by d lambda. Let's write it down, and you have this dd of lambda, and here you will have e to the power lambda omega, right? Okay, let me just again put a side note. Lambda is a scalar parameter and omega is a matrix or an operator, whatever you want to call it. And we want to find this derivative term. So the first thing I'm going to do is that, as you know from previous lectures, we can define exponentials of a matrix or an operator. So let me just write this down, but now I'm using the summation notation so that I can get a compact information in very less space. So this will be lambda n omega n divided by n factorial. And notice that this sum starts from 0. So if you recall that if you had an operator like this, the first term was identity, right? So what does this tell us about this identity term is that the zeroth matrix, that is omega to the power 0, will be considered as the identity. This is a definition. This is a definition. Because taking a matrix and giving its power 0 is something that is not well defined. You can think of right now that, hey, whenever its power is 0 for numbers, let's say you have a number 5 to the power 0 means 5 to the power m divided by 5 to the power m, where m is any number you want, and these two cancels each other out, and that's why you get a 1, right? But for matrix, this division doesn't make any sense. So that's why you have to think this omega to the power 0, that is a matrix to the power 0, is equals to identity, and this is a definition or axiom, whatever you want to call it. So you have to accept that in order for this exponential expansion to work. Otherwise, this expansion will never work. So now this is a summation thing, right? And these are my omegas. So now what I'm going to do is that we are taking derivative with respect to lambda, right? But omega is something that doesn't depend on lambda, so we can safely extract this matrix out over here. So in the next line, what we're going to do is that we're going to put omega outside and we'll keep it in front, because if we put it in the right hand side, it might seem that the derivative will work on the omega as well, but that's not the case. So let's write omega first, that is my omega to the power n, right? And let's try to take the derivative. So it will be dd of lambda sum over n equals to 0. Okay, let me put the summation sign in front so that you don't get confused. And now what you have is lambda of n by n factorial, right? And then again write the sum omega to the power n. And if you, now these are just scalar parameters and you know exactly well how to get the derivative of it. This is just n into lambda to the power n minus 1, right? And now we are technically done, but to put this whole thing in a closed format, that is, you can simplify it more, what we're going to do next is that we're going to break this factorial. So n factorial can be written as n minus 1 factorial times n, right? We are going to do just that. So if you write 0 to infinity over here, n equals to 0 to infinity, that is, and you will have omega to the power n, n minus 1 factorial. There will be another n, and there's a n in the denominator as well, and you have lambda n minus 1. And from here, let me just write it, use the space over here. Now what we see is that these n's get cancelled out and this omega of n remains. And note that the summation is starting from n equals to 0, but if you get n equals to 0, this will be minus 1 factorial. So what we're going to do now is that we're going to take one of the omegas out. That is, let me just write it down and then it will be clear to you. So we are taking one of the omegas out. Now we are going to start the summation from n minus 1. So the idea for this is that when n equals to 1, the denominator will have a 0 factorial, which is defined to be 1. And if you just start from n minus 1 from 0 to infinity, now let's see what happens. N minus 1, and here you will have lambda n minus 1. This is a number, so you can put it anywhere you want. And since we took out one of the omegas, the omega to the power n will reduce to omega to the power n minus 1, because omega and omega, they commute. Anything commutes with itself. So as a result, omega of n minus 1 times omega is just omega to the power n. So these are the crucial things that you need to be careful of, but you will get used to it. This might seem very weird at first, but you'll get used to it. So look at this guy over here. So let me just highlight it, what I'm talking about. That is this guy, enclosed with the second brackets. This looks very similar to an exponential function, provided it starts from n minus 1. Since n minus 1 is a dummy variable, so let's just change n minus 1 to m. So we are taking n minus 1 and we are replacing it with m, since this is a dummy variable, and this gets summed over. So if you do that, you will have omega sum over m, where m starts from 0 to infinity again, and you will have lambda to the power m, omega to the power m. So this means replacing all the n minus 1 with m, and this is a dummy variable, that's why it doesn't matter, and m factorial. But this is what? This is simply the exponential of the lambda omega. That is, if you just look at these two lines, that we came from this line to this line, right? Using the definition of an exponential of an operator. the exponential expansion, and we are getting the same thing over here. So finally we can write omega, and the thing in the parenthesis is nothing but e to the power lambda omega, right? So what we got finally, we got dB by d lambda as this thing, right? So dB by d lambda as omega e to the power lambda omega. But b was what? B was e to the power lambda omega, where b is a function of omega, lambda itself. So let me just write it down explicitly, and this will mean this. So finally you can write dB of lambda, d lambda is equals to omega b of lambda, where everything is operator. So these are operator valued equations where you are taking derivatives and doing all these manipulations with operators. And the reason this is very crucial is that this is a differential equation. Note that this is in fact a differential equation. This is an operator valued differential equation. And operator valued equation. And in physics, most of the time we will deal with this kind of things, and knowing their solution is crucial. So since we got this differential equation starting with b that was defined as this guy over here, we can say that this is actually a solution. That is, so let me just write it down, and let's call this equation as equation 1. So conversely, we can say that if you are comforted, that is whenever you are dealing with a differential equation that looks like this, that is equation 1. So any equation operator, I forgot to write operator valued. Any operator valued equation as similar as 1, if you are dealing with it, the solution, that is b of lambda, is of the form b of lambda equals to some constant over here, because this is a differential equation, right? And if you are familiar with integration, that is the inverse of this differential operator will be an integral operator. So we're going to put an integral operator over here, and let's take the limits to be 0 to lambda prime, some lambda prime, that is you are integrating over the parameters, and this c will be determined from your limits. That is, instead of 0 to lambda you can have numbers, let's say from 0 to 1, 2, 3 or whatever, and this is the form that we are dealing with. And finally you can write it as c times e to the power lambda omega. So this c is actually coming from this integration thing, nothing else. So this is how you can even solve operator value differential equations as well. And let me before I finish off, let me try to show you why these kind of discussions are important, because in quantum mechanics we have the Schrodinger equation as I h cut d psi dt as the Hamiltonian and psi. So this is an operator value differential equation as well, because this Hamiltonian operator is nothing but the energy operator, schematically speaking, yes, and this psi will correspond to some state. And this equation governs how the system evolves in time, because in quantum mechanics, time is just a parameter. So whenever we are interested in how things evolve in time and we want to use quantum mechanics for that, this is the equation that we will refer to. And this is a operator valued equation, and in fact it will have solutions something like this: e to the power minus I h t. In fact, h here is still an operator, and this is some initial state, that is psi of 0. So psi of 0 is kind of equivalent to psi of t. Sorry, psi of t0. That is the initial time. So that's why we want to discuss this kind of operator valued functions and operator valued differentiations or integrations and so on. So this will be it for today, and I'll see you guys on the next lecture. Thank you.